The next speaker is Tatiana Galochkina from Bigger Lab, and with a talk entitled MEDUSA, Deep Learning Based Protein Flexibility Prediction. Tatiana, you can start.
Thank you very much. Sorry. Okay, so today I would like to present you the other project we are working on in our team, which deals with the prediction of the protein flexibility from amino acid sequence. Sorry. So as you all certainly know, and we have seen it one more time during the previous presentation, proteins are the highly dynamical molecules. And the flexibility of different protein regions would determine such important properties of the protein as its stability or interaction with the other molecules, for example, with other protein partners or small drug molecules. Therefore, information about the flexibility profile of protein is very important for different domains such as drug design or protein engineering. So in practice, how can we describe the flexibility of a protein? There are some experimental methods which provide us with the flexibility indices. The most common one would be B-factor, which is available for the majority of the resolved protein structure when we use X-ray crystallography, and which reflects attenuation of X-ray scattering due to thermal motion. Despite the availability of this index for a lot of protein structures, it has some fallbacks. For example, first of all, and most importantly, it depends strongly on the experimental settings used for crystallization. And in case we have highly flexible fragment in the protein structure, most probably it will not be crystallized at all. So we will have zero information about the degree of flexibility for this fragment. So the second most used parameter for experimental flexibility prediction would be the NMR order parameter, but still it will depend on the experimental setting. And in case of NMR, it will be available only for rather short proteins. Finally, there is a possibility to obtain a more detailed view of the protein dynamical properties using molecular dynamics simulations. However, all the three methods that I listed are rather expensive, both in terms of resources and in terms of time used to perform an experiment. Therefore, neither of them is convenient for the large-scale studies of protein flexibility. So the goal of our project was to suggest a data-driven method for prediction of the protein flexibility profile directly from amino acid sequence. As a descriptor of flexibility, we have chosen the classical one. We have taken the normalized B-factor values, and we have performed prediction in several ways. The first one, the binary prediction. So we put a threshold on the B-factor values and predicted if a given protein residue would be considered as flexible or rigid. And we have also considered two multi-class problems. So predicting the classes extra rigid, rigid, medium, mostly flexible, and very flexible in order to provide a more detailed view on the protein flexibility profile. And here is the workflow that we followed during the development. So the first part was to choose the encoding that would extract the maximum information contained in the protein sequence. And to do so, we have considered 4 different descriptors. 3 of them are the descriptors of individual amino acids. The basic one-hot encoding of each amino acid, so just translation of the amino acid in a profile of 0 and 1s. The flag, which indicates if it's a real amino acid or the end of the sequence. And we have also used the physicochemical descriptors, which were derived and chosen to be the most this representative of all the physicochemical descriptors and called the I indices. They correspond basically to 58 values describing such properties as hydrophobicity or charge of each amino acids. And finally, in order to take into account the evolutionary information contained in the amino acid sequence, we have also introduced the position substitution specific matrix profiles. That is, basically, we have performed the search of the homologous sequences of the protein, thus making part of the same protein family. And we have calculated the expected frequencies of each amino acid for a given position in the protein family. So taking all this information together, we have concatenated it in vectors of descriptors, which were finally of 100 descriptors per position. And in order to take into account the environment in which our residue is located, we have used the slicing windows of 15 amino acids, where 15 amino acids described by 100 features would thus describe the central residue. And the data in this form was used as the input data for the prediction tool that we have developed during the second stage. So we have decided to use the deep learning model for our predictions, since they have demonstrated pretty good results for diverse bioinformatics problems, and also for the similar ones, such as secondary structure prediction or protein-protein interactions prediction. After trying several architectures, we have finally chosen the pretty classical one. So it is a 3-layer convolutional neural network with the varying size of the kernel, and the last dense layer finally leading to the classification of our results in 2, 3, or 5 classes in our model. And we have estimated the performance of our models in 10-fold cross-validation. That is, we have split the data set, which was non-redundant in terms of sequence similarity. So our data set consisted of a sequence sharing no more than 25% of sequence identity. We split it in 10 independent subsets and perform training and testing each time, leaving off 1/10 of the total data set. Furthermore, in order to make sure that there is no even remote homology between the test data set and trained data set, we have imposed an additional filter by structural similarity. That is, we have made sure that in our test data set, there is no protein ID with the ECODE value close, the same as any protein in the trained data set. So using this procedure, we have estimated the performance of our model and compared it to the state of the art tool. We have performed the comparison on the same problems that were used in the initial publication. So the tool of reference called ProfBeval, and it was published as early as 2006 by Schlesinger and Rost. And they treated 2 binary classification problems, with the first one called strict and the second one called non-strict, which differ by the threshold that we put to decide if the residue is rigid and flexible. The consequences of this choice is the ratio of flexible residues in our dataset. For example, in the case of non-strict case, we have fixed 50-50, we have the same number of flexible and rigid residues, while in case of the strict threshold, the number of flexible residues is below, and therefore the data set is imbalanced. So what we have seen during our performance evaluation is that we outperform ProfBeval for both problems for at least 2% at balanced accuracy. And moreover, if you take a look at the confusion matrices, we can see that our method, MEDUSA, performs similarly for both a strict and non-strict model. So it's not dependent on the number of flexible residues in the data set due to class weighting that we use during training, while probable for the strict problem significantly overpredicts the rigid residues in the data set. And to go further, we have also implemented the more precise flexibility prediction in 3 and 5 classes. And you can see that the model trained in the same way as for the binary classification demonstrate decent performances for this much more complex problem. And at least all the predictions are located close to the diagonal, and we observe very few errors of extreme type. Very rarely we predict the extremely rigid fragment as the very flexible one. So what are the application of the prediction we made? There are several of them. First of all, the very flexible regions are often associated with the protein conformational transition and can be the hinges governing these transitions. Here is the example of the calmodulin molecule, which is a well-studied example. And we know that calmodulin undergoes the transition upon calcium binding, and the mechanics of these transitions is governed by the folding in the middle region. And using only the sequence information, MEDUSA is capable to correctly identify this exactly region participating in the calmodulin transition. The second very interesting example are the disordered proteins. For the proteins, we do not have any determined fold. And while MEDUSA was not trained to recognize disordered proteins, so no disordered proteins, of course, were not added to the trained data set, it still successfully identified the locally rigid fragments. So here you can see this is the local deformability profile as it is calculated from the NMR structure of the disordered protein. So the lower the value is, the less this region is deformable in the initial structure. And here is the result of the prediction with the disorder prediction tools. And here is the result of MEDUSA prediction in 5 classes. So you can see that for all the 3 regions, which are locally non-flexible, locally rigid in the case of disordered protein, MEDUSA successfully identifies them. Even more, for the last region, even the disordered tools do not provide such a coherent result as MEDUSA does. That is, MEDUSA can be potentially used to complement the disorder predictions in case we expect the protein to be disordered with known sequence. Finally, the MEDUSA can be used to estimate the impact of different mutations on the protein flexibility. Here there are 2 examples of the stabilizing mutation, one for the xylanase. So here is a set of stabilizing mutation which were induced, and MEDUSA successfully predicts the slight decrease of the protein flexibility in this fragment. And here is only 1 point mutation, which also induces the rigidification of the protein fragment. And once again, MEDUSA does capture this subtle change. This is another interesting example of 2 homologous proteins, which have the pretty different sequences. But since MEDUSA takes into account the evolution information and takes as input the PSSM profile, we can see that the majority of the flexibility profile is almost the same for both sequences, and it's recognized by MEDUSA correctly. And moreover, the difference in protein flexibility comes from the very flexible C-terminus fragment for the second one, and MEDUSA also does correctly identify this flexible fragment. Yes, I'm very close. So the complete pipeline is implemented in one program, which is available on GitHub with the source code, and also as a web server with a user-friendly interface, so which we invite you absolutely to try. It just takes as input to the sequence you would like to analyze, does the search of homologous transformation of the input data in the form expected by the model, and returns you the nice visualization of the prediction results with overall pie chart of the ratio of flexible residues and the general flexibility profile. So I thank you for your attention. Here is the link to the server, and here is the publication with the more detailed analysis of the results that I just presented. Thank you.
Thank you, Tatiana. We have one question. Can you, from C. Maroon, can you detect loops? And can you detect bit conformational change like in ZERPIN?
Okay, so basically we do not, what MEDUSA predicts is the expected flexibility. So certainly most of the time when you will see the flexibility profile for the folded protein, it will be very rigid for alpha helices, very flexible for the loop. The larger is the loop, the more you will have a peak in the flexibility profile. So yes, at some point we detect the looped region in the structure, even though it's not the direct information from the MEDUSA output. And big conformational changes, we cannot, unfortunately, MEDUSA cannot tell you what kind of conformational change is associated with the region which is described as flexible. But once again, if you expect that there is some large conformational change that takes place in the protein and you detect the peak of flexibility on the MEDUSA profile, it will be an indication that the residue responsible for this change are located here. I hope that answers the question.
Okay, thank you. Is there another question? Waiting, I have one. Is there a limit on the size of the protein?
There is one. To be honest, I have forgotten on like 1,000 residues. I think we put it like this. It's the only limitation is the computational time it takes on the server to do the homologous search. So basically in the algorithm, there is none. On the server, we have had to put some limit just not to let people wait in the queue for too long. But in the standalone version, you have the code, so you can easily change or eliminate this restriction at all.
Okay, thank you. Other questions? No, I don't see questions. So we can go to the next speaker. Thank you, Tatiana.
Thank you.